Today I'm gonna recap the analysis of the least square estimator real quick. So last time we talked about the two important properties of the least square estimate. The first one is that the estimator is unbiased. All right, its average, its ensemble mean is actually the true parameter. And the second one is we have derived the covariance of the of the regression coefficients. But when it comes to a special case, that when the noise when the noise corrupted in the ground truth model, or the term we will use, data generating process, if this noise if this noise is IID and has a uniform variance, which is sigma square, okay, under such assumption, it doesn't have to be normal, sorry, like I should have said that these are IID, okay, and the variance is the variance are equal to sigma square. Under such assumption, we can show that the covariance of beta hat is sigma square x transpose x inverse. All right. So there's a derivation last time. Okay, please review. So today I'm gonna also present another important property of the least square estimate. It is optimal in the sense that it attains the minimum covariance when the noise are independent, or you can say when U is white noise and has the unit covariance. Okay. So in this analysis, we will show that the covariance of beta hat, the least square estimate, when you compare with another estimator, beta hat, all right, where the beta hat is also unbiased estimate, we will say that the covariance of other estimate is always bigger than the covariance of the least square estimator, which means this is a favorable result, right? Because you attain the minimum covariance one. Again, this result is referred to blue property because it's best in the sense that your least mean square has a linear form of estimator. It is linear because your beta hat is a linear function in y. Okay, it also unbiased because of because you're going to compare among the unbiased estimators. Okay, and it's optimum in the sense that the covariance is smallest. Okay, the way we show this is very simple. Okay, so assume that beta hat is another estimator, another unbiased, and it's in the class of linear. So we assume the form of other estimator as matrix beta times y, where you leave the matrix B as arbitrary. Okay, so in order for beta hat to be unbiased, okay, beta hat it has to satisfy this condition that E of beta y, E of B times y must be beta in order to be unbiased. But E of by is, now you're going to use data generating process equation, all right, which is b times x times beta, right, plus e expectation of u, which is 0. So in order for the equation beta times x times beta equals to beta, in order for this equation to hold so that this estimator is unbiased, so we end up with the equation with a condition that b times x must be identity matrix. Mathematically, this means the matrix B has to be left inverse of x because it's left multiplied with x and it gives identity matrix. Okay. For the linear least square, we have seen it before that the least square estimate is linear in Y, right? Where the matrix gain here is in a particular form, all right? And we already showed that, oh, this is the left inverse of X, because if you multiply with X, it gives identity matrix. Okay. Secondly, when we characterize the covariance of beta hat, of course, is a covariance of B times Y, right? And and this is equal to, from the analysis, this equals to B times covariance of Y times B transpose, because this is F5 transformation in Y. What is the covariance of Y? Okay, so Y equal X beta times U. Covariance of Y, okay, please work it out. Covariance of Y is going to be covariance of U. This is deterministic. This is constant. We assume that the noise has a unit covariance. It's a multiple of I. So here is identity matrix. So it's B transpose. Okay. Now we would like to show, this is what we would like to show. Now I'm gonna arrange the covariance of beta hat with the following term. We know that the covariance of the least square estimate is sigma square times X transpose X inverse. But in this example, I mean, it's okay. It doesn't lose any generality that we assume that the sigma square is 1. All right, just normalize it. So sigma square is 1. Then, of course, this quantity is also equal to the above equation because the factor on the left and on the right hand side are also identity matrix. So we rearrange in that term with the purpose that, of course, right now, the covariance, if you pick out this term and this term, the yellow and the pink term, and then you subtract covariance of beta hat square, least square from any other estimate. You see that you have a common factor on the left, which is B. You have another common factor on the right hand side as B transpose. Okay. From this result, it gives us a very important interpretation that, okay, first of all, it's in the form of B times a matrix here. Okay, we call it, it's in the form of I minus P, B transpose. Okay, you call this guy P. What is this matrix P? We have seen it before. This is what? Orthogonal projection matrix, right? It's actually this matrix P is a matrix that map from Y to give the prediction in Y hat. Okay, refer to the previous slide. Okay, it's here. Okay. Okay, if you just plug in the form of X transpose X inverse X transpose Y, right? So you see that Y hat is in the form of P times Y, and that is the orthogonal projection matrix. Okay, from here you see that this is a quadratic form of the quadratic form of B. Then we know that first of all, what do we know about I minus P? Okay, I will let you verify, because this matrix P is orthogonal projection matrix. So it satisfies 3 properties. First of all, it's symmetric. Second of all, it's idempotent. All right, P square equals P. This condition has a meaning that, okay, you multiply Y, the original vector, to get the Y hat, right? You project it. All right, you project it to get Y hat. But if you multiply Y hat to P again, which is P square Y, Okay, the resulting projection would be the same vector. Okay, which is what? If y hat is already on the space that you projected to, of course, if you make the projection again, you should give the same vector, which is y hat. Okay, so that's the meaning of orthogonal projection, that it has to satisfy this property, p squared equals p, or idempotent matrix. The third property can be shown as well. The norm of the projected matrix vector px, the norm px is always less than the norm of the original vector. Okay, from the last bullet. What's the meaning of the third property? Of course, this is original vector, the yellow one. When you project it on some subspace, the norm of the pink vector cannot be bigger than the norm of the original one, because the pink vector, all right, must be added up with the blue term to get the yellow one, right? So the py plus e must be equal to y. So of course, the norm of py cannot be bigger than the norm of p, and that's the meaning of the third property. The third property mathematically says that the norm of px squared less than the norm of x squared. Okay, if you change it to transpose, right? All right, so the norm square is the inner product of that vector with itself. Okay, now can you characterize this multiplication? Sukit, px transpose px is
x transpose p transpose px.
This, right? Now Panat. Now, if P is orthogonal projection matrix, P has the first and the second one property. So P transpose P equals
to P ครับ
equals to P, right? Okay. And then if you just move around, all right, just move around the inequality, you get x transpose I minus p x bigger than 0. This holds for any x, which means this implies that the matrix I minus p must be positive semi-definite. Okay. So this is a basic property of any orthogonal projection matrix, which means when we come back to this slide, this guy is always positive semi-definite. If you pre and post multiply by the factor b and b transpose, the result is also positive semi-definite. Again, the meaning of this interpretation is that if you compare the least square estimate with any other linear estimator that is also unbiased, the covariance of other estimator always bigger than the covariance of the least square estimate. These hold again under the assumption that the noise corrupted in the data generating process, these noise are uncorrelated, right? Because the term I use white noise here, it means that the EIJ and EUI and EUJ is 0. And also, it has a uniform variance. The variance of UI, this is equal. They are all equal, all the components. And in this proof, the proof actually, it doesn't depend on the scalar value of the variance, so I assume it's to 1. Okay. You can assume it without loss of generality. Okay. So in short, we say the least square estimate has a blue property. Panat, question? You can ask because because it's a small class. You don't need to raise your hand because sometimes I don't look at the monitor. Just turn on your mic and ask.
โอเคครับ
Mm.
If any beta hat is not unbiased, it means that can be a lower covariant than the beta hat from least square, right?
Usually is not of interest to compare with the bias estimator, because again bias
But it is possible, right?
It is possible, but the analysis here will go through again because it doesn't follow the same way. But again, if you compare with bias, right? So let me put this in scenario. Suppose this is least square estimate, right? It's unbiased. But again, suppose you can pick another one that is biased, right? But the covariance of beta hat, it turns out to be smaller, right? Is that the scenario you make assumption?
Yes, อาจารย์
So I'm asking, I'm saying that it could be possible because the analysis here also assume this property of other estimator to be unbiased. But I'm saying that even you have that result, still is not a fair comparison, because even though other estimator is better than least square in the sense that it has smaller covariance, still it is biased. So you have one advantage, but you still have one drawback here. So my point is, in most of the analysis, that's why they compare only among unbiased estimator.
Okay, thank you ครับอาจารย์
Okay. I think last time I skipped this proof, but I mean, of course, the concept is very, very important. You will also okay, and now I would like to mention that the result we say on this page last time, okay, it requires some exercise to prove as well, okay, because based on that results of the covariance of beta hat. Remember that the covariance of beta hat is sigma square x transpose x inverse, right? But again, sigma square here is a noise variant that is typically unknown. So that's why in practice, we will use an estimate. Okay, this is an estimate of the noise variance. And in most software, okay, we use the residual sum square divided by n minus n small n. And we can show that it is unbiased estimate for the true variance. Okay. Okay. Did we talk about accuracy? Not yet, right? Okay. So, okay. I mean, this quantity is, I mean, this is standard and very common. You see that this quantity already available in any return result from the linear regression command in MATLAB or in Python or in R. Okay. We can show this in the section where we can discuss about the lab and numerical problems. Okay, but in the meantime, I think you can try, if you use MATLAB, you can use fit-lm, all right, and see the manual guide on how they return the results. I'm saying that it return everything. It return residual, it return residual sum square, it return this thing, okay, estimate of the noise variant, return the covariance of the estimator. Okay. Okay. So once you have solved the linear regression, of course, you need to examine the accuracy of the model. One of the indicator to measure that is R square. R square is a quantity that based on this total sum of square decomposition. It says that the total sum square, TSS, which means it measures the measurement It measures the the distance between the measurement and the average of the observations. Y bar or the mean of Y actually represents the simplest way of predicting your response. I would like to refer to this the simplest model. If you have y1, yn, right? You have the n samples, and I'm thinking about the simplest model, simplest linear model. The simplest one would be I want to fit it with a constant. All right. So in a vector form, right? Just a constant. So it means that I have data point, right? I want to fit it with a constant. What that constant would be, okay? That is beta 0. And in terms of the vector form of the regression, my vector X regression matrix would be a matrix of all ones. Okay. Another part, my beta hat would be the closed form. What is it? Napat.
X transpose Y.
Okay. But with this simple model that I make, this is constant model. My A is the vector of all ones, right? Now you're gonna plug it back. And I've simplify this expression. 1 transpose 1 is N. N, big N, right? So it's 1 over N here. What about 1 transpose Y?
Is the sum of yi.
It's the sum of yi. Okay. Which means if you fit a constant model to a response variable, that optimal constant is basically y bar, right? It's very intuitive. What would be the best prediction if you don't use any predictor at all, right? Use the average. So that's why when I come back to this TSS again, okay, it's just the way that you measure the error between the response and the output of the simplest model, which is y bar. Okay. It turns out that algebraically, this total sum square can be decomposed into 3 terms. The second term is called residual sum square. All right, that measures your y, your actual y with the y hat from your regression model. Okay, the explained sum square, that's measured between your y hat and the mean. Okay, now we have the latter term. The latter term is the inner product between y hat, right, and y hat minus y bar. Okay, when you run linear regression, and if your regressor matrix contains all ones in the first column, all ones means you fit, which means that you fit a constant in your linear regression as well. All right, that's why you have all ones here. If that's the case, we can show that this term is always 0. Okay, you can prove it, which means we can write TSS as RAS plus ESS. Okay, and then the R square is defined by the portion of ESS with respect to total sum square, or on the other hand is 1 minus residual sum square. For the residual sum square, of course, for a good model, you prefer it to be small, right? You prefer the deviation of your model output to the actual y, you refer this guy to be small. Okay, so that's why the indicator R square, the larger the better, and we can prove that in this with this assumption, the R square is between 0 and 1. Again, this is a mathematical proof here. Okay. So it's basically a portion of the actual y that can be explained by your model. Again, R square is also returned in the software. We have other indicator as well. I will explain later. Adjusted R square. You may have heard it before. Okay, that will be discussed later. In this last topic, I would like to discuss about the problem of identifying significant variable. Okay, so when we have many many predictors included in the model, in the regression model, one of the question is to test whether beta k is 0 or not. Because if beta k is 0, is believed to be 0, it means that your variable xk is not significant. It should not be included in the model. And this is how the statistical test is performed by using the null hypothesis as this. And of course, the alternative is beta k is non-zero. Okay. The test statistic they commonly use is the t statistic. Okay. So they compute beta hat divided by the standard deviation. And that is called standard error in the context of linear regression. Okay, of course, I will come back here, right? I will come back here. So this is we mostly apply to this expression to approximate the covariance of beta hat. Of course, the beta hat is a so if beta hat is a vector in Rn, the covariance is a matrix of n by n, all right? Sukrit, if we want to get the variance of beta hat, what components of covariance do we look for? This is the matrix covariance. If we want to find the variance of beta hat, how can we get it from the covariance matrix? Variance of beta k hat.
Diagonal.
At the diagonal, right? So at the kk element, that would give the variance of beta k hat. Okay. That's why we look at the kk elements of the covariance matrix, all right, and then take the square root, which represent the standard deviation. We normalize it in this way, and we can show that this is distributed as t distribution with n minus n degree of freedom. And again, this can be proved, can be shown if you can show this result. Okay. And that require Gaussian assumption in the DGP as well, require that the noise is Gaussian. Okay. So of course, the test statistic has t distribution. Okay. When you perform a hypothesis test, you compute the p-value. That is a probability of the t variable bigger than this, bigger than the magnitude of the absolute value of this test statistic. This is compute from the data, all right. And if the p-value is smaller than a significant level, and this is up to you. The default one in the scientific software is 0.05. Then we reject the null hypothesis. Okay, if we reject it, that would mean that the corresponding variable is significant. And that is how we can basically interpret the results returned by the software. Recall to advertising data. Okay, remember that we have sales and we have 3 channels of spending advertising budget: TV, radio, and newspaper. Okay, on the top row, I run the regression on one variable. I regress cell on radio, just radio, one variable. And in another regression, I regress cell on the newspaper. Okay, so when you see the results here, okay, that's a table return. First of all, the p-value, if it's significantly smaller than alpha, that means the corresponding variable is significant. Okay. How can you read from the coefficient? That is beta 0, that is beta 1 hat. Okay, so from here, so it means that radio, the data of the radio, it means that the amount of money you spend on the radio. So it means that if you spend in the radio if you spend 1,000, all right, the cell would be increased by 0.2 or 3 times 1,000, which means the cell would be increased by 103 units. Okay. When you perform the single regression, we see the results that both a newspaper and the radio are significant. On another regression model, now I include all the variables, all the predictors at once: TV, radio, newspaper. Look at this result. Okay, now look at the p-values. Do you see anything? Do you see anything insignificant? Kilowatt. Look at the p-value. P-value, if it's bigger than alpha, which one?
The newspaper.
Newspaper, right? So if alpha is big, if p-value is big, it means that if we fail to reject the null hypothesis. Corresponding variable is insignificant. Okay. But then it comes to the, okay, and we leave that for now first, okay, but let's see the way we interpret the coefficients. Okay. So for example, the coefficient of TV, all right, so it means that if you spend like 1,000 on TV while holding other variable fixed, so the cells would be increased by 46 units, right? Now look, go back to this result. Is it possible that when you run a simple regression, the newspaper is significant, right? But when you run a multiple regression, when you include everything, the newspaper becomes insignificant. So it's kind of contradict, right, between the simple regression and the multiple regression, the results. Now, if we explore further, we look at the correlation matrix. Okay. The cell is a response, so TV is X1, radio is X2, newspaper is X3. Okay. Now we focus on the newspaper. What happened to the newspaper? Now we see that newspaper and the radio, okay, among the predictor itself, the newspaper and the radio has some correlation, 0.35, all right, which means these two variables, they both have the same trend. The market that has a high newspaper will tend to have also high budget spending on the radio as well. Okay, in the multiple regression, of course, as we see previously, the newspaper doesn't seem to have an effect on the cell, right? Because of this p-value. But from this correlation matrix, it just gives us interpretation to explain such a contradiction. So it means that whenever newspaper is high, right, it doesn't directly increase the cell, but the trend that the newspaper is high will also give a high trend of the radio as well. And the radio, that is the actual important variable for the sales to be increased. Okay, so which means actually the newspaper actually get the credit for explaining sales, but that credit, it comes from the fact that the newspaper okay, has a correlation with another predictor variable, which is a radial. All right, I think this is an interesting example they bring up in the book. All right. In the next couple slides, I will give this lecture later because actually this is a very important questions about deciding important predictors. How can you in this example you have 3, right? The question would be, suppose you have n predictors in in your candidate choice. How can you include only subset of them? How can you decide which one is significant? And we have other methods to discuss the best subset stepwise regression, all right, or some shrinkage method or regularization technique like lasso. Okay, but we wait until we explain about the concept of model selection, and we come back to this topic.